Welcome back. Before we move on to doing some mathematical analysis, what I'd like to do is to give you a real example of just how useful generalised Newtonian models can be. This example dates back to when I was doing research in polymer processing at Cambridge and when I was involved in a project that embedded miniature tubes within thin plastic films, a product that was called microcapillary film, or MCF. As the project progressed, we were experimenting with different die designs, and one day we got a very unexpected and somewhat surprising extrusion product. What we wanted to do was understand why this had happened. But before I tell you about this unexpected product, let me introduce you to the MCF extrusion process. Now, any extrusion process, as we've seen before, starts life with an extruder, so I'm not going to draw a diagram of extruder because you've seen diagrams of extruder quite a few times now. What I will show you, however, is the important part of the process, which is extrusion die. So this is the extrusion die simplified in cross-section, and it's a very simple die. It's like a simplified film casting die, but very narrow. So it's just simply a converging channel that gives a planar product. That planar product is a film somewhere between 15 and 20 millimeters wide when it's undrawn, and when it's drawn down somewhere between 5 and 6 millimeters wide. Now, placed within the extrusion die is an injection head. That injection head is streamlined to fit within the extrusion die and consists of effectively an air conduit. So the outer part of this injection head is connected to atmosphere. And this injection head effectively consists of a metal body into which are brazed or shape-formed what look like hypodermic needles. In the first instances of the die, they were hypodermic needles. Latterly, these were spark-eroded and plunge-eroded tubes fabricated from one stainless steel block. So that if you look at the die end-on, what you see is a die exit, and that's sort of outlined there in yellow, with a row of air injectors. Now, the action of the flow over these air injectors suck air in as you get that change in direction over the injector tips. It causes a low pressure. That low pressure is lower than atmospheric pressure, and because there's continuous connection between the end of those injectors and atmospheric pressure, airflow results. And the sort of product that you get, I've put a picture of there on the whiteboard. And it's great because it's a very elegant, very regular product. In this particular example, the width of this product is about 6 millimeters. There are, I think, 19 holes in this particular product, and each hole is around 200-250 microns in diameter. And so we were looking to innovate a process that took the guesswork out of foaming, the nucleation part being the guesswork. And so what we were doing was we were strategically introducing voids within a polymer in order to change its properties. And this was the method that we'd innovated to do that. And as the project progressed, we were changing the design of the injection head. We started off literally with small bore hypodermic needles corresponding to that row of blue circles. And the diameter of those hypodermic needles was sufficiently smaller than the breadth and width of that slot. However, as time progressed, we wanted to see, can we get bigger channels? Can we introduce more voidage? What percentage of voidage can we introduce? And so one of the ways we did this was to increase the diameter of those injection nozzles, such that they more closely resembled that diagram that's there on the screen. So there's actually quite a tight tolerance between the wall of the plain die and the outer diameter of each of the injection nozzles. And when we did that, what we found was an extrusion product that didn't have circular holes in, but had diamond-shaped holes in. Diamond-shaped holes through the middle, and sort of arrow-shaped holes at each edge. And we looked at this under the microscope and were, frankly, amazed. And that amazement was very quickly followed by the question, why? How? What fundamental physics is responsible for this change in shape? And we were thinking about, well, it's obviously a viscoelastic effect. It's got to be. It's going to be some sort of stress relaxation process. I mean, it can't surely be explained just by the fact that we've got shear thinning happening. But what we wanted to try and do was use the computer modelling at the time to gain insight into this. And there's some very, very good lessons to be learnt through what we found from this and how to use computer modelling. I think now that computational power is cheap, people tend to dive into computational modelling to the most complex model they can find and see if they can answer a problem without actually stopping and thinking sufficiently beforehand. When computational power is expensive and hard to get hold of, you have to think very, very carefully what question it is you're asking and what result it is you're trying to achieve from a model. So let's just go through that logic. We're going to use model not to try and describe a whole process, but effectively to eliminate or to include pieces of physics that may or may not be responsible for an effect. And so the aim of the model was to try and come up with some explanation and some insight into why diamond-shaped holes had been formed in this polymeric product. So, any model has limitations. Computational power, 20 years ago, was one of the limitations that we had. And viscoelastic calculations for a complex geometry, for a complex rheology, simply weren't going to happen. Not unless you had a very large budget and a very large cluster and a lot of time. And so we had none of those. So we had to try and answer the question using a simpler formulation of a model. We couldn't do a viscoelastic calculation, so let's invert the problem and say, well, how much of this effect can we explain using simpler physics? How much can we explain using a Newtonian model? How much can we explain using a generalised Newtonian model? And so what we did is to say, well, look, let's realise our limitations. Let's see what we feasibly can run in a complex geometry. We can run a generalised Newtonian fluid model that'll give us a shear thinning behaviour that is comparable to the polymer that we've measured experimentally in terms of its rheology. And that should give us an idea of how much of the phenomenon we're seeing is due to shear thinning alone, and then anything that's not there is due to some physics that we haven't included. It might be a time-dependent stress effect, it might be a viscoelastic effect, it might be something else. But we know that it's not the physics that we have included. And so it's sort of proof by exclusion in a sense. So what we did was to create a model using a generalised Newtonian rheology, a Karo-Yasuda rheology, because that was the constitutive equation that was built into the code we were using. And we fitted the Karo-Yasuda model to temperature-dependent experimental rheometry. So we described the rheological response as a function of shear rate and as a function of temperature. The code that we used was a code called Polyflow. That code is now part of the ANSYS suite, and the version we used was Polyflow 3.10. Now, one of the advantages of Polyflow at that time and now is that it has been specifically developed to try and predict extradate shape. It doesn't use some of the volume of fluid or level set approaches that, say, Rheotool or OpenFoam use, but it uses a mesh deformation kind of approach where you can get some incredibly accurate results where that phase boundary between solid polymer and the outside world isn't blurred by, for example, not having a refined enough mesh because you're trying to capture a two-fluid problem. It is not a two-fluid model. And so effectively what Polyflow allowed us to do was to do a deformation calculation. You define a mesh that includes your die and your product, and you put some boundary conditions on it, and it'll figure out how that mesh deforms such that those boundary conditions are honoured. And the key boundary condition is what happens in atmosphere. There's no stress on the surface. So what happens to that stress? Therefore, how does the material respond? And also, with shear thinning, how does the flow distribute in a complex die? So, the model we made, cutting a long story short, enabled a visual representation of the deformation of the material. And I've put that visual representation on the whiteboard for you there. And this took, back in the early 2000s, quite a long time to calculate. And when we looked at that result, we were astonished, equally astonished almost, as we were by the physical result under the light microscope. And if you look carefully at that computational result, what you can see is, okay, I'm not going to say perfect consistency to the experimental result, but a huge amount of similarity. You've got diamond-shaped holes. If you look carefully, you've got the wavy nature of the surface.
If you look at the edges, you've got the more arrow-shaped holes, and you've got that little notch on the external surface as well captured. And so, to a reasonable level of confidence, we can say this has got absolutely nothing to do with viscoelastic or time-dependent effects. We're completely wrong. It's all shear thinning. And this has all been described to a phenomenal level of accuracy using a generalised Newtonian fluid model that is readily available within a computational code, that is easy to regress to experimental data. And what great insight that was. So, let's summarise a few key points. Generalised Newtonian fluid models are very, very useful. Their utility extends beyond estimating a pressure drop or beyond estimating a shear rate, because some numerical codes will allow deformation calculations to take place. And, as I've illustrated with this example, a generalised Newtonian fluid model will allow you to understand what part of the deformation in an extrude is due to shear thinning and what is not due to shear thinning, the physics that you haven't included. And so it can be incredibly effective, or it can be an incredibly effective way of describing practical observations. Generalised Newtonian fluid models are so much simpler to solve computationally than fully three-dimensional viscoelastic models. They're simpler to fit to experimental data, they're simpler numerically to set up, and they're quicker. And so, as a first pass or a first estimate to a problem, it's a very, very useful thing to do. And now that compute power's relatively cheap and quite powerful, it's a very quick thing to do. So, don't forget how to ask a question. In this particular case, we wanted insight into a phenomena. We wanted to try and achieve that insight in the quickest and simplest manner. And the quickest and simplest manner was not by trying to go for a fully fledged model that included every single physical effect. We went for the simplest model that we could to get fundamental insight relatively quickly and relatively easily.